Hello, Tensor friends. The last couple of videos, we've been looking at the derivatives of vectors. So the first one we did, we derived how a basis vector is defined as the derivative of a position vector with respect to a coordinate. So we went through all that. We had a good time, blah, blah, blah. Then the next one we did, we were using the multivariable, the chain rule, and looking at vectors as operators, I'm sorry, basis vectors as operators. And we learned how to go all the way through this mess and define a position vector entirely in polar coordinates. All right. So now we're going to step up to curves. So we want to look at the change in a position vector with respect to arc length. Now, it is basically the exact same definition, except instead of adding delta x's to the definition of a derivative, you're adding small changes in arc length, right? So the position vector is a function of arc length. All right, so let's go look at that. Okay, so we're in desmos.com. All right, so I just have a normal grid line here, the coordinate lines. I want to define a circle with a radius of, looks like 2. And now on this circle, I want to define a point. So I use our transpose equations, which is r cosine theta and r sine theta. Okay, because as I mentioned before, Desmos won't let you work in polar coordinates. You have to use your own transpose equations. So now we can define a point, and there it is. Now, from the origin to that point, I can define a vector r. So this is our position to vector. Now, this position vector is a function of this angle, right? Because here it is in the transpose equation. So everything's in radians, by the way. As I change that angle with respect to this coordinate line, you see that position vector, it changes. Now, what I want to do now is add an increment to this angle, just an increment, right? And define a new point up here. And I see that it's already too close. All right, let's move it away. So I'm just increasing this increment away from this point here, right? Now that will define a new vector, all right? And both of those are going to change in tandem with the angle reference to this coordinate line. Okay? Now, in following that equation we looked at first, we want to know what is the difference between this vector and this vector is a new vector, and it's that one. Okay? And you can see as I change that increment of the black one away from the red one, the distance decreases, obviously, and that is given by that orange arrow, and it eventually becomes the same vector. Okay? Now, what we want to do is to finish that equation, we have the vector and increment away. We have the original vector, and we have the difference, which is the orange vector. Now we need this arc length. All right. So to calculate that arc length, we need this angle and that angle, right? Because S equals delta theta times R. Remember that? All right. So here is the angle to the red vector. This is in radians. And here is the angle to the black vector right there. Okay? Now, if I take, here is my delta theta, so that's the change in those two. And so the arc length in this case is 1. This arc length here, wherever I set this, so if I change that increment away, you see the arc length increases. Okay? So it's as simple as, to finish that equation, we just take this vector, which is what? The difference between this one, and divide it by the arc length, and we get a new vector, and it's the blue one. Okay? Now let's start reducing the small increment change we put in like this, and look what happens to the blue arrow. It goes all the way down until I can't get any closer and it becomes undefined. Okay, so this blue vector now is the S hat, the unit vector tangent to this curve at that point. All right, so let's get some of this stuff off of here so we can play with this one. Let's get rid of that one too. Now, if we lay that red vector all the way down like this, you can see that this is a unit vector, right? So it's 1 unit long, and it is tangent to this position vector as a function of arc length. So that little blue vector there is S hat. And it turns out this little rascal is fundamental in some of the work you do in tensor calculus. And that's why I want to introduce it like this. And the next time we'll actually do something fun with it. All right, I'll see you later.